a research engineer at Robotics Research Center at IIIT Hyderabad, and he is working with Professor K. Madhava Krishna on scheme representation for robot, focusing on out-of-distribution generalization. He has graduated in 2022 from BITS Pilani with BE in Electrical and Electronics Engineering and M.Sc in Chemistry, and he will be joining UT Austin in the fall this year as a graduate student pursuing MS in Electrical and Computer Engineering. So over to you, Raghav. You can present and you can start your presentation.
Yeah.
Yeah.
Good evening, everyone. Thank you for the kind introduction. I'll move on to my presentation. I hope my screen is visible now.
Yeah, it's visible and you're audible
Yeah.
as well.
Okay, so I am here today to present our paper Anticipate and Collab as already introduced. This paper is currently under review at IROS 24 and it has been accepted at a cooking robotics workshop at ICRA 24, which will happen in May. So let's go through the basic motivation of a paper. The basic motivation is that if a human and a robotic agent are collaborating in a household environment and they wish to accomplish some task in a home like preparing breakfast, cleaning dishes, watering the plants, etc., then many of these tasks require some common subtasks which can be executed in parallel. And for instance, if the agent needs to move to a different, for instance, if there is a common pantry room which contains the washing machine as well as some food supplies, and the agent needs to go there for to get the cooking supplies and also to put the clothes for washing, then the agent there's a common subtask of moving to that room for different tasks. So the agent can actually move there, like reduce the number of trips to the room by moving once and executing the common subtask in parallel. So if the agent can anticipate and collaborate with the human based on the previous pattern that it has seen in the household, then it can be more efficient in its task execution. So let us demonstrate this with the help of an example. Let us look at the figure on the right. Here the blue circle represents the human and the green circle represents the agent. And the task here is that human is trying to cook an egg and the agent has been asked to serve juice on the dining table. So since the agent is asked to serve juice on the dining table, the agent just has to move to the fridge, pick up the juice and move to the dining table to serve it here. Whereas human is doing a cooking task, so the human first moves to the countertop, picks up a metal pot, brings it to the stove, then the human moves to the fridge, picks up the egg, and then brings it to the stove and continues with his cooking task. Now this required 4 movement steps on the side of the human and 2 movement steps on the side of the agent. And while the human is cooking, the agent is standing idle because it hasn't been asked to do anything else. Now, but because the agent can see the human performing its task in the home, the agent can actually anticipate what the human might be doing. So if we look at the anticipation scenario on the figure on the left, then here the human moves to the countertop to pick up the metal pot, and the robot moves to the fridge to pick up the juice. But because the egg is also in the fridge, the agent can pick both the items together, and when it comes to serve the juice, it can move over to the stove to provide the egg to the human. So in this way, while the human is picking up the metal pot and bringing it to the stove, it will already have the egg ready for him as the agent brings it over here. So we demonstrate that both the human and the agent can reduce their overall cost of execution in the home if they can anticipate their upcoming tasks and prepare for them together. So the framework that we demonstrate is called data plan, and we say that our framework data plan leverages generic knowledge encoded in LLMs for task anticipation, uses an action language to encode fine-grained domain-specific knowledge of a household environment, adapts a classical planner to compute a sequence of actions that the agent executes and the human is expected to execute. So here, when the agent anticipates upcoming tasks, the agent can plan its actions of how to achieve those tasks. And while doing that, the agent also expects that which of these actions would be done by the human. But the human and the plan that the agent computes, it contains the action that it will execute and the expected actions that the human is expected to execute. And lastly, we see that the human is likely to deviate from the actions expected by the agent. And in that case, the agent automatically adapts by replanning or generating new task predictions. So the action language that we talked about in point 2 over here, we use a language called as Planning Domain Definition Language or PDDL. So what this language, so on the left we have just have a map of the environment that we're working in. This map has been created in two simulation environments. One is Copilot Sim, which is a like a robotics real world like simulation environment where we have spawned our robot and we perform simulations to see. And another is we have created a similar domain in PDDL, Planning Domain Definition Language. So in PDDL, we define a domain in the form of the state space and the action space possible in the environment. So we define all the different types of objects that can exist in the environment and all the different states in which the objects can be. So for example, let us look at this particular example of an action move. This is just a syntax in which actions are defined in the language, where an action move will have some parameters. So for instance, if the agent needs to move, then the parameter would be the ID of the agent that is making the movement. The precondition would be that the agent needs to be at an initial location I, and the effect would be that the agent would end up moving from the initial location I to the end location G. So this is how we define actions in PDDL, and we also define different states, and actions move the agent and the entire environment from one state to a different state. Then this is how we define the domain. Then we define a particular problem where we define all the objects that are present in the environment at a given moment, the initial state in which the entire environment in. This would encompass all the initial location of the agents as well as the initial state of all the objects in the environment. And the goal state would be the final state we want the environment to be in. Then we use some classical planners that take this initial and the goal state and find a sequence of actions which will take the environment from the initial state to the goal state. So let us go through the problem formulation. We have two actors, human and robot. The objective is that they have to complete a task routine, which is a sequence of high-level tasks. Each task belongs to a set of known tasks, such as making a bed, preparing breakfast, preparing salad, etc. But each of these tasks is further divided into finer granularity actions, which would be like moving to a place, picking up, putting down, turning something on, etc. The task for planner is that it needs to compute a plan, which is a sequence of actions which take the environment from the initial state I to the goal state G. Many such plans are possible based on the different actions executed. But the optimization algorithm for the planner is that it needs to find the optimal plan pi star, which reduces the total cost C pi, where the total cost C pi is given as the individual cost of CMR plus CNH. So here CMR is the cost of executing MH action by the agent R. We use the term robot and agent interchangeably here. So R is the robot, H is the human. CMR is the cost of executing action AM, and CNH is the cost of executing action AN by the human. So this is the total cost for both the human as well as the agent. And the task for the planner is to find the optimal plan, which is the lowest cost of the total system. So let us go through the individual steps of our framework one by one. First, we have an LLM prompting environment where we give an example. So for instance, here, the total task list, which is the global set of tasks which are possible in our environment, are provided to the LLM to keep it grounded to our environment so that it does not hallucinate. Then some specific user preferences are also provided. And then the scene description of the current state of the environment is provided to the LLM. We provide this along with a in-context example of how we want the LLM to respond. This information is provided to the LLM, and based on this information, the LLM anticipates upcoming future tasks in the environment based on the previous information that it has seen. So LLM generates a set of tasks that it feels needs to be executed. And in case of hallucination, we incorporate a feedback which goes back to the LLM and to keep the LLM grounded in a current domain so that it does not anticipate any tasks which are not possible in an environment. Once the tasks are anticipated, they are mapped in the form of goal states for the PDDL language. So here each task is mapped to a specific syntax of a goal state. For instance, here prepare a meal boiled egg is mapped to boiled egg goal state. So the domain which contains all the state and action space and the problem which contains the goal state is provided to a planner. We are using a planner known as the fast downward planner, and the goal for this planner is to find an optimal plan which takes our system from the initial state to the goal state. So this is a joint plan that is computed by the planner. So now this planner contains actions corresponding to both the agent as well as the human. As we can see, agent pick up raw egg, human pick up receptacle plate 2. So these are actions corresponding to both the actors in an environment. However, the agent will execute all of his tasks, but the human tasks are not deterministic. The human may deviate from his actions based because the human will not expect is cannot be expected to execute all the actions as anticipated by the agent. So this joint plan is then provided to the simulation environment where the simulation happens. And in case there is any deviation on the side of the human from the expected plan, then the feedback for replanning happens, and this goes back. So there are feedback in two settings. One setting is where the human preferences itself change. So for instance, if the LLM anticipated a sequence of actions, sequence of tasks that need to be executed, but the humans' preferences have changed and there is an urgent need for changing in these plans. So in such a case, for instance, here we give an example that if there's a fire in the kitchen, then the sequence of task execution needs to be changed. Then this human provides the feedback, which goes back to the LLM to prepare a. So LLM now receives the current state of the environment and also the prompt provided by the human. And based on this information, the LLM generates a new set of anticipated tasks. The second form of feedback that we consider is where the human deviates from his actions as generated by the agent. And in this case, the feedback goes back to the planner. So for instance, if the human was expected to pick up a particular item, but the human did not pick it up, or the human ended up doing something else, then that feedback would reach the planner and replanning would happen, which would incorporate the action taken by the human, and a new set of plan would generate from the given state, and the execution will continue. So let us go through the experiments and the hypothesis we propose in the paper. The first hypothesis is that LLMs can accurately anticipate future tasks based on a small number of contextual examples. Many recent papers have demonstrated that LLMs are good at pattern recognition and summarization techniques. So for instance, um, if when we have to train any learning model, we require a large amount of data to learn. But LLMs have been trained on a lot of uh, world data, which give them a sense of common sense reasoning, which allows them to learn patterns in a household based on a limited number of prompts. And some papers have also shown recently that LLMs are able to um, create plans for executing actions in a home. So here we are not using LLMs for planning at the level of actions. We are using LLMs at the level of tasks, high level tasks, which the LLMs are anticipating based on the pattern it has seen. So we create a data set of high level tasks such as cooking, cleaning a room, washing clothes, washing dishes, etc. And then we create different task routines for two separate households. Each of these household has a different pattern of executing tasks. One household may prefer to wash clothes in the morning. Another household may prefer to wash it in the afternoon or the evening. So the pattern of executing tasks is different in each of the environment. And we perform the experiment where we give information of the household based on a limited number of prompts using in-context examples. And we experiment if the LLM is able to anticipate tasks and able to recognize a pattern of task execution in that environment. So we use three different LLMs, Gemini Pro, Claude 3, and GPT-4, with few in-context examples, with and without chain of thought reasoning to anticipate the next four tasks in a routine. To measure their efficiency, we collect human expectations, which has been collected through a survey, and we use these human expectations as the ground truth for LLM evaluations. Uh, we use the following metrics for evaluation. The first metric is the mean overlap. So for instance, if the ground truth uh, task anticipated by the human is GI and LI is the task anticipated by the LLM, then the intersection between GI and LI is uh, is considered for the metric mean overlap. Then the second metric, or the second and the third metric that we use, is greater than 50% and greater than equal to 75% overlap. So here what we do is we take the intersection of GI and LI and we see that if that intersection is greater than or equal to k. So for okay, let me explain this slowly. We are using the LLM to anticipate next 4 tasks in the home. So if the human also anticipates next 4 tasks, which is considered as the ground truth, the LLM also anticipates 4 tasks. So mean overlap is measuring the mean of the task anticipated, the common task between the human and the LLM anticipations. Whereas the greater than 50% overlap measures that if the human was asked 100 times to anticipate the next 4 tasks and the LLM was asked 100 times, then out of 100 times, how many times they had at least 2 tasks common out of 4 tasks. So that is greater than 50% overlap. And when there are at least 3 tasks common between the human and the LLM anticipation, then we call that as a greater than 75% overlap. So when the value of k is 2, then this is greater than or equal to 50% overlap. And when the value of k is 3, then this is greater than or equal to 75% overlap. Here I is an indicator function which gives the value 1 when the condition inside it is true, and it gives the value 0 when the condition inside it is false. So as I said previously, we prompt LLMs in 2 settings. One setting is just providing in-context examples, and the second setting is chain of thought reasoning. So here is an example of how we are prompting the LLM. We first provide the task sample space. This needs to be provided as a JSON dictionary. This is important to provide because when we do not provide this is the total sample space of tasks which is possible. If we do not provide this, then the LLM is very likely to hallucinate tasks which are not possible. So for example, in our environment, we are constrained inside a home. So we do not consider tasks like going to a grocery store or tasks like that. So we do not want the LLM to anticipate tasks outside of our domain. So hence we are providing a sample space of tasks as a JSON dictionary. Then we provide some routines of tasks happening in the household with 2 sample observations. So these observations just show the sequence in which tasks were executed in the previous 2 days in the home. Then we provide the LLM with an input prompt. Here it is provided with the initial state in the form that it is an evening time and the previous task that the user has given, prepare casual clothes. And then we ask the LLM to anticipate the next 4 tasks along with an urgent task condition which describes the current state. So for instance, the requirement here is that the kitchen is very dirty, and then we ask the LLM to anticipate the next 4 tasks. So here is an example LLM output provided here. So in this setting, we have provided the task sample space and 2 observations based on which the LLM finds the pattern of task execution. The next setting that we explore is chain of thought reasoning. So chain of thought prompting is a method where LLM, while providing in context example to the LLM, we also provide a reasoning method on how to understand the data provided in the observations. So for instance, here, uh, so in this case, we would provide observations along with a chain of thought reasoning of why these observations make sense. And then when the LLM gives the output, along with the output, LLM provides a chain of thought of itself. So for example, here, the task was prepare casual clothes and the next 4 tasks were required. So this is the sample output provided by Claude, where the output is that the LLM thinks step by step on how to anticipate. So here it says that the user has just come from office and prepared their casual clothes. From the previous observations, we know that it is that in the evening the user typically prepares and serves dinner, takes their medicine, and either stores the leftover food in the fridge or throws it away. This is the pattern it has observed from the previous observations. Now it also sees that the current state of the environment states that the kitchen is very dirty. So it says that the kitchen is very dirty. So before preparing dinner, the user will need to clean the kitchen. So the anticipated tasks are clean the kitchen, prepare a meal, serve the food, and prepare medicines. So these are the 4 tasks it anticipated, and this is the reasoning that it provided for these 4 tasks. So this is based on the paper Chain of Thought Prompting Elicits Reasoning in Large Language Models, and this has been explored by lots of papers that are using LLMs for their applications. So let us look at the results provided here. So as I said that we prompt this for 2 separate households. So these are the results for the first household. Let us look at the first example, first figure on the left. This is for the mean overlap. The blue bar shows with few shot prompting, in which case we give a few in context examples. And the brown bar here shows the LLM output in the presence of chain of thought prompting. So we can see that chain of thought prompting improves the efficiency of LLM for all the three LLMs considered. And then the next is greater than or equal to 50% overlap. So here we see that in the presence of chain of thought prompting, each of the LLM reaches a value of 1. So what this means is that out of the 4 tasks anticipated by the LLMs, at least 2 are always matching the human expectations. These results are averaged over 25 separate experiments, and we see that the value is 1, which in the form in the presence of chain of thought prompting. So at least 2 out of 4 tasks will always be matching the human expectations. For the greater than or equal to 75% overlap, we also see similar results where Claude reaches a value of 1, which means that out of 4 anticipated tasks, 3 are always matching the human expectation, which means that LLMs are able to find pattern in the household execution and are able to accurately anticipate upcoming tasks. We also show that in this example, in each of the 3 cases, Claude is outperforming GPT-4 and Gemini in the presence of chain of thought prompting. Then these are the results for household 2. Here the results also show the same trend where chain of thought improves the efficiency, but the results are not exactly one here. And this also shows that the pattern in which tasks are executed depend on the household itself. So for instance, the household 1 that we had created was a more uh, ordered household where tasks always happened in a very fixed order. Household 2 was not that orderly, so that is why there is a lack of efficiency while anticipating upcoming tasks. So with this, we close hypothesis H1 and show that LLMs are able to accurately anticipate upcoming tasks in a home. Our second hypothesis discusses the advantage of anticipation. So what we say here is that considering anticipated tasks as joint goals reduces the plan length and the plan execution time compared to considering one task at a time. So here, every action has a cost associated with it. That cost represents the time it would take to execute that action. So we say that when we are considering anticipated tasks as joint goals, then the overall execution time goes down. So how we perform this experiment is that we increase the number of anticipated tasks from 0 to 4. We are, as discussed previously, we are using the fast downward planning system, which is a classical planner. And we compare the performance of our framework data plan with that of a classical planner, which only computes sequence of actions for one task at a time. So we compare the performance for one system which only performs one task as it is provided to a different system which computes plan for a given task as well as the set of anticipated tasks. So these are the results here. So on the left y-axis, we have the ratio of execution cost, and on the right axis, we have the ratio of plan length. Let me explain this figure slowly. The uh, blue fixed line shows the cost ratio for household 1, and the dotted lines show the ratio. Dotted blue line shows the plan length ratio for household 1. So the two metrics here are execution cost. Execution cost, as I said, is the time it would take to execute it, and the plan length is the number of actions it would take to execute it. So for both of the cases, let us just look at the straight line first, the blue straight line and the orange straight line. So for both of these, um the execution cost is going down as the number of tasks anticipated increases. So here, 0 means no task anticipated. So that is the agent which performs task as it is provided to it. So it performs one task at a time. And 1 means the agent that perform plans for a given task and one task ahead of itself, and so on. So we increase the number of anticipated tasks from 0 to 4, and we see that the overall execution cost goes down as well as the overall plan length goes down, and the same pattern is observed for both of the given households. Uh, with this, we close hypothesis H2, which shows that anticipating upcoming tasks results in a lower execution cost. Uh, our next hypothesis discusses the advantage of collaboration. So we say that human-robot collaboration results in a more efficient goal attainment compared to no active collaboration. So in this case, we conduct paired trials with and without collaboration. So in one setting, the human and agent are collaborating with each other, and in another setting, they are performing their independent tasks without collaborating with each other. And we evaluate this over two separate settings. One is where the human is faster, and one is where the agent is faster. So we want to show that overall collaboration is beneficial for our environment, whether and we also show that this is the case for different initial states and for different types of settings, whether the human is fast or whether the agent is fast. Here the metric we have used is called zeta, which is defined as the ratio of execution cost with collaboration and the execution cost without collaboration. And if the value of zeta is less than 1, that means the execution cost with collaboration is lower, and that denotes effective collaboration. So let us look at the results here. So here we consider the experiments are conducted with different initial location of the human and the robot. So because the task distribution in the home is skewed, so a lot of not the task distribution, sorry, the object distribution in the home is skewed. Sometimes more number of objects can belong to a particular room. So the initial state sometimes plays a big role in defining the overall execution cost. So that is why we consider 16 different cases where the initial location of both the human and robot are varied, and we consider two different settings: human fast, agent slow, and agent fast, human slow. And we show that in all of these settings, the value of zeta is less than 1. The lowest zeta has gone is 0.747, and because the value of zeta is less than 1 every time, this is a mean over 50 trials, and because the mean value of zeta is less than 1, we say that collaboration between human and agent leads to effective reduction in cost, and it is better for the environment in terms of the overall time taken by both the actors to complete their task. Uh, we also show this in the form of a video. This is the same example as was originally shown in the first figure. Here the green is the agent and blue is the human. On the right hand side, they are performing their task without anticipation and without collaboration, and on the left hand side, they're executing it with collaboration. So on the left hand side, we see that when the agent picked up the juice to serve it on the counter on the dining table, and at the same time, the agent came to the counter to the stove to help the human in his actions. So on the left hand side, the total cost was 381, and the plan has finished, execution has finished, while on the right hand side it takes longer time to finish, and there's more idling time for the agent and the human. With this, we'll close the hypothesis H3 and show that collaboration is effective for our environment. Our last hypothesis here is hypothesis H4, which states that when the human deviates from the expected plan, then the agent is able to adapt to these changes. And we show this in two different settings. The first setting is that when the human's preferences changes, so as discussed initially, um, agent anticipate a set of tasks for the given home, but the set of tasks may differ on a particular day based on a specific scenario. For example, if guests are coming over, or if the human has to go out for dinner, then the anticipated tasks will change. So during the execution of tasks, the human can interrupt the agent with a prompt, and we perform re-prompting at that setting, and we show that the agent is able to adapt to these unexpected changes when the human preferences change. The second experiment is when the human deviates at the level of actions so initially the agent expects the human to perform a given set of actions, but when the human deviates from those actions, then we want the agent to monitor when the human has deviated from the actions, and we also want the agent to adapt to those deviation, and the agent adapts it while through replanning. So first result is for hypothesis H4A, which says that when the human preferences changes, then the human can interrupt the task execution for the agent, and the agent can reprompt and generate a new set of anticipated tasks. So this is the result where we see that like there's a 98% accuracy in. So this results are similar to how H1 was conducted, where the overlap is computed with human expectations, which was collected and considered as the ground truth. And 98% mean overlap has been observed for Claude with the human expectation, and 91% for GPT-4. The second experiment is when the human deviates from its expected actions. So for this case, we initially generate a set of actions which the agent will execute and the human is expected to execute. Now randomly we introduce errors in the pickup actions of humans. So the human is expected to pick up a particular item. It may not pick that item up, or it may end up picking up something else. So these randomly introduced errors are monitored by the agent in the environment, and the agent replans at every point of deviation. So, so we are able to show that in any number of uh, errors introduced in the pickup actions, our framework is able to adapt, and we are able to execute the entire plan by replanning. But what would happen had we not uh, monitored and had we not adapted to the deviation? So the figure over here shows that where this is considered as the baseline, where the agent does not adapt to the deviation from the human. So here there are the different number of tasks that the human and the robot are performing, and uh, the column show the number of errors introduced in the system. So and the figure and the values here show the percentage of tasks or the fraction of tasks which are able to which the entire system is able to complete, and we show this in the form of mean and standard deviation over different number of experiments. So for instance, if we look at row 1 here, when there is one task, and so when there is only one task that needs to be performed, and even if there is even one error introduced, then the overall that task is not completed. So the number of tasks completed is 0. In the second scenario, there are two tasks that need to be executed, and one error has been introduced in a pickup action. So we say that the overall value is 0.5, which means that out of two, one task is completed. When two actions have error, then the overall efficiency, the fraction of tasks completed are 0.25. So basically, and this is a standard deviation of 0.25. So basically, we are saying that 1/4 of the task would be completed in this scenario, and so on. Whereas our framework, when it performs, it is able to consider these erroneous outcomes, and it is able to adapt, and we show a successful execution. We also show this qualitatively in the form of a video. Uh, Yeah. So here the agent and the human are performing a task where the actions are shown over here. The agent brings juice on the table. Then the agent moves to the top, puts down egg, picks up boiled egg. So the expectation here is that the human would bring a plate for the agent to serve. But the human deviated from the plan and the human ended up carrying a glass. So our agent adapts to this deviation from the human's actions, and the agent replanning happens. Agent moves to the rack, picks up the plate itself, and brings back to serve the boiled egg on the table. With this, we complete hypothesis H4 and show that our framework is able to adapt to unexpected changes. With this, we conclude our paper. So the main conclusion is that LLMs are able to anticipate high-level tasks on a household based on pattern recognition, and we show that chain of thought reasoning increases the LLM efficiency, and we show that Claude 3 outperforms other models with chain of thought prompting. Then we say that classical planners like fast downward will always produce, not always, but they produce accurate and correct plans. So the setting that we explored is satisficing setting. So we do not go for the absolutely optimal plan, but we go for a satisficing plan which results in a lower cost reduction. So this is like a trade-off between the computational resources and the planning cost. And then we say that when jointly planning for current and anticipated tasks, then we demonstrate a 25% reduction in execution time and 17.4% reduction in plan length compared to when we are not anticipating the upcoming task. Then we say that human and robot can effectively collaborate with each other, resulting in an overall cost reduction of 25.3% as compared to a setting where both the actors act independently without collaborating with each other. Lastly, we say that interruptions and deviation of human from the expected plans can be well accommodated by our framework. None of this would be possible without some of the really good work which has inspired our work. And with this, I conclude the presentation. Thank you.
Okay. Thanks for this nice talk.
Thank you. Yeah.
So if there is any question from the audience, they can ask. Okay, I think nobody has any questions. So I have a very basic questions like
Yes, sir.
when these LLMs are kind of, I mean, maybe I'm not able to follow it. Like when LLMs are kind of anticipating something, how the agents are understanding that, or the LLM is inbuilt in the agent, or
No. So, okay. So, for example, whatever the task were anticipated by the LLM, it is like it is mapped in the form of goal state, which is provided to the agent. So the agent computes this plan, and the LLM's tasks are mapped to this. So this has been done using a normal. So because our task list is closed, we only perform a closed set of
okay,
tasks. So these are mapped to every task anticipated by the LLM is mapped to a given goal state for the
okay,
agent.
okay. So agent will only perform the task that will be written in this problem.pddl file, right?
Yes, it is a closed set of tasks for now.
Okay,
Yes.
okay. So agent can't anticipate new kind of this
No, no.
task. I mean, it will
Yeah,
be
for
pre-fixed.
yes.
Okay.
So in this scenario, we are considering this form of prompting only, where the set of tasks that it can anticipate are fixed. So we are also providing the LLM with a global sample space of tasks, and it will only ask to limit itself from these tasks.
Okay. And is it possible that agent can also predict new tasks? I mean, in the literature, is it possible?
Yes, so it can always anticipate new tasks, but the problem is that the way the classical planners work is that we
Hmm.
properly describe each and every action space and state space for their environment. So if we want the agent to
Okay.
perform a new task, which it currently does not know, then
Hmm.
the classical planner will not be able to incorporate that because it needs a formal definition of the actions that it needs to perform. So every action
Okay.
here is considered as a proper, I think there was example here. So every action is
Oh.
defined like this, that it has proper set of parameters, preconditions and effects. So for
Hmm.
example, if there was an action to cook stuff on the stove, now if
Hmm.
the LLM anticipates a task which requires cooking in a microwave, which is not currently defined in a domain, then
Right.
our classical planner will not be able to incorporate that. But a
Okay.
recent few works have proposed that they are generating new set of actions using the LLM
Hmm.
itself. So LLM
Oh.
provides the task as well as description of the actions that need to complete that task. So in that scenario, that is possible.
Okay. Okay then. Since no one has any other question, let's thank again Raghav for this wonderful talk,
Thank,
and
thanks a lot for
let's
having me.
close this talk, and we'll meet again next week.
Yeah,
Thank you.
thank you.
Thank you.
Thank you,
Bye.
everyone.